Yes. Okay. So linear programming, that is the 12th chapter, last but one chapter. And what are we going to do in this chapter? So what is the significance of this particular chapter for our exam as well as in a real life? So let's see. Okay. Yes. So what do we have? Linear programming. Let's understand the definition of this first. A linear programming technique is used to find the best outcome in a mathematical model with a linear relationship. Let me explain what is it. So first, let me read out the points here. So linear programming helps in solving the real world problems involving the decision making and resource allocation. So it is an optimization technique in which a linear function is optimized. So this is very important. A linear function is optimized, that is either minimized or maximized, subjected to certain constraints. What are constraints? The limitations, okay, which are in the form of equations. In this chapter, we shall study some linear programming problems and their solutions. So what do you mean by this information is, in a real world problem, in a real life, we might come across a lot of so problems we need to solve to in order to achieve some progress. For example, you are working in a company and that company has some particular target to achieve, a profit target maybe. So and they also have there is some losses as well as profit. So generally, we tend to increase the profit and tend to limit the loss or reduce the loss, right? So let a loss be represented by a linear equation. Okay, so then what is the objective will be to minimize the loss. Similarly, let the profit be represented by a linear equation. Then what is the generally objective of the uh, profit will be to maximize the profit. Along with that, whenever you have involved with a profit or loss, there are other things which will affect. So those are called constraints. For example, resource allocation. Maybe the budget of a particular process will be limited. We'll be limiting the budget to say some lakhs or some millions. And then we also talk about the available resources. So these are called constraints. Okay, so by converting all these constraints and then objectives into linear functions, we try to plot them on a graph and try to understand the whether we can get the objective achieved or not. So the objective functions, whichever is there, either maximizing the profit or minimizing the loss, whichever, what we do, get by achieving the objective or optimizing the required objective, we solve the problem. So this is called optimization. Okay. So what is optimization is getting either generally getting a higher profit, possibly the highest possible profit with the given constraints, or reducing the losses with the given constraints. Okay, there is an example for whatever I said right now. There is a very important, interesting example here. Let me show you how we can formulate this situation in terms of linear programming. Okay, so let me read this situation here. Can you please read it once? I'll give you 5 minutes. Uh, Not 5 minutes, maybe you can take 1 minute to read this completely. Can you please read it? After that, I'll explain the situation to you again. Yes, please read this example. A furniture dealer has a budget of 50,000 and a storage for maximum of 60 items, that is either table as well as chairs. The table cost 2,500 each and the chairs cost 500 each. He makes a profit of 250 for every table and a profit of 75 for every chair sold. He wants to determine the optimal number of tables and the chairs to buy within the budget to maximize the total profit. So this is very important. What is our objective now? To maximize the total profit. So this is a classic example of an optimization problem and aimed at maximizing the profit. So I'll show you now how can I imagine this as a linear program problem. Say our budget, let us first establish the unknown variables. Let x be the number of tables we have to buy. Okay, y be the number of chairs. Okay, so how are we going to take these unknown variable which have to be fixed, right? So it's a, because it's a linear one, we will have only two variables, okay, in the two-dimensional and with the degree one. Okay, so it's a linear program, right? So first condition what we have is every chair cost is 500 and every table cost is 2500. So total cost cannot exceed 5000, 50,000. So first equation what we can have is 2500 into the number of chairs, 500 into number of yeah, this is table, this number of chairs less than or equal to 50,000. So if I simplify this by dividing by 500, what I get is 5x plus y should be less than or equal to 100. So this is one of the constraint, okay, based on the budget. Next, what we have is he makes a profit of 250 for each table and sold at and rupees 75 for each chair sold. He gets a profit of 75 for each chair and 250. So that is the optimization function. So that we have to maximize. So the maximization, we usually represent the objective function as z. Here it has to be maximized, which is 250 for every table and 75 for everything. This is our objective function. Okay. Apart from that, what else we have is the number of chairs and number of tables cannot be exceeding 60. So that is x plus y should be less than or equal to 60. This is another constraint. Along with that, we always have a positive constraint, that is the number of chairs cannot be negative and it should be more than or equal to 0. Similarly, y, that is number of tables, also cannot be less than 0. That has to be more than or equal to 0. So these are the functions, the linear functions, which are going to be used together to optimize the given condition, that is optimize and get the highest profit possible. Okay, so I will come into in detail of this. Right now, try to understand the significance of this particular function in this situation. Okay, so how to solve this? How are we going to optimize? What do you mean by optimize? We are going to arrive at that particular value of x and y, which will give you the highest possible, in this case, maximizing the profit, right? So maximized profit. After that, we'll say this is the highest profit we can achieve. Now, do you understand the significance of this in the real life? Definitely, it has a lot of application, but it is restricted to linear function only. Okay, so let's see how they have solved this particular problem. Okay, so there is a solved example, same question. We are solving it. Let's see. Okay, let us solve some questions. I'll come back to the same question later, that particular example later. So let us solve some basic questions based on what we have learned here. Okay. The first question goes like this. Can you please read it and try to answer this? Which of the following is not a vertex of the positive region bounded by the given inequalities? Okay, first, before solving any of these things, let us keep our basics clear. In a linear equation, I'll bring back to the example which I took previously. We had this condition. One of the condition was 5x plus y less than or equal to 100. Am I right? Yes. Next, what we had is x plus y should be less than or equal to 60 and x should be greater than or equal to 0, y should be greater than or equal to 0. So these four things are constraints. And the objective function was maximize z is equal to what? 250x plus 75y. This sort of condition was right. So imagine you're plotting a graph for this. Okay. So imagine you're plotting a graph for this. So the graph is going to be like this. So I'm just roughly drawing a graph here for your understanding. So as it is inequality, we have to show the feasible region, which is feasible region means the region where the solution exists. Okay. So as we are going till 100, let me give the unit like this. 10, 20, 30, like that. Maybe 20. I'll go for 20, 40, 60, 80, 100. Just for easy units, as we cannot draw the bigger graph right now. This is 20, 40, 60, 80, 100 along the x-axis and y-axis. This is the first quadrant. This is second quadrant. This is the third quadrant. This is the fourth quadrant. You know, in the first quadrant, this origin. In the first quadrant, both x as well as y is positive. In the second quadrant, x is negative, y is positive. And here it is negative, negative. And here x is positive, y is still negative. Right? So our constraint says x is greater than or equal to 0 and y is greater than or equal to 0. So whenever we have a positive constraint, our answer will be only in the first region, okay, first quadrant. So far our region will be here. This is where we are going to get the solution, okay. But we have this line 5x plus 1. So if you know how to solve, how to plot linear equation, it is good. Or else we will imagine this first as a linear equation, and we will find out where it is cutting the x-axis, that is x-intercept. X-intercept is the point where it cuts x-axis at y equal to 0. When y is equal to 0, what is x? 20. That means this is where our line cuts x-axis. At x equal to 0, we get y-intercept. At y-intercept, at x is equal to 0, y will be what? Equal to 100. That means this is where we have. So that means our line is going to be going through like this. Okay, yes. So our line is going through like this. And look at this. It is saying less than or equal to 0. Less than or equal to 0 means let's see the feasible region. This is called half of the entire plane is divided into two halves now. One half is on the right side of the line, another half is on the left side of the line. As it is giving this particular inequality less than or equal to, we have to just check an easy point, any particular point in this equation and see whether it is lesser or more. So very easiest one, if the line is not passing to the origin, it is better to substitute the origin and check. If you put x is equal to 0 and y is equal to 0, we get 0, which is less than or equal to 100. That means our region is on this side of the equation. So our particular region is on this side of the equation. Just remember, our particular region will be completely on this side of the line, including this part. Okay. Apart from that, we have one more line, x is equal to x plus y equal to 60, right? Yes, I'll come to that now. That's very important again. So if next one is x plus y less than or equal to 60, we can treat it as a line now. So if x is equal to 0, y is equal to 60, y is equal to 0, x is equal to 60. Same way we're going to draw another line, 60 and 60. So if you draw the line passing through 60 and 60, we get another line. And again, this will have a restriction on this side, right? So finally, even this way, we have x greater than 0, we'll have equation here, and y greater than 0, we'll have equation here, and our complete feasible region is here. So these are called corner points. I'll come to them later. For now, let's yes. Let's now focus on our problem for this particular question right now. So this is a point where yes. Just a second, just hold on. Yes. Yes. So coming back to this, now where is our feasible region? Our feasible region is here. This is the This is the corner points, and these are called corner points. By substitute defining these particular point where what is x and y, we will understand which one of these particular corner points will give you the maximum result. So that particular point is called optimization point. Okay, and if we substitute that, if you particularly maintain those values of variables, will wind up achieving the highest possible target or the lowest possible target based on the our function or objective. Okay, so now this is an example. We'll come back to the same example later. So, or we can just see, check these values at this particular point. What is x is? X is 0, y is 60. And at this particular point, y is 0, x is 60. And at this particular point, we just have to solve these two equations. What are the two equations we have is 5x plus y is equal to 100. X plus y is equal to 60. Okay. So when you subtract, what happens is 4x is equal to 40. So x is equal to 10. So x is equal to 10. So this particular point is x is equal to 10. And when x is equal to 10, what happens to y is, if you put x is equal to 10, y will become 50. Right? Yeah. So y is going to be 50. The last point what we have here is this one, which is 0, 0. So now we have to now observe there are 4 places where x is equal to 0, y is equal to 60, x is equal to 60, y is equal to 0, x is equal to 10, y is equal to 50, and x is equal to 0, y is equal to 0. 4 corner points. Now we can already understand which one will give a maximum answer by looking at this. Still, if you substitute the values in the given objective functions, what is our objective function? What is our objective function? 250x plus 75y equal to z, right? Now I need to maximize this. So which will give you maximum answer? Suppose if you put x is equal to 0 and y is equal to 60, what we get is 75 into 60, right? So what is 75 into 60? So which can be written as 300 by 4 into 60 without calculator if you want to do. So 15 into 3, 45,000, 4,500. Okay, so that is one of the value. Similarly, if you put x is equal to 60 and y is equal to 0, we get 250 into 60. Okay, how much is this? So which is 150, that is 15,000. If you try this, it is 15,000. So when you go for x is equal to 10 and y is equal to 50, what happens is 2,500 plus 75 into 50. 75 into 50, we get 25, 5 sevens are 35, 37, which is 3750. So which is completely giving you how much? Which is giving you 6250. So out of all this, which one is giving you highest values? This value, where x is equal to how much? 10, y is equal to 50. So right, so that is, this is a point which is our objective, which is where our objective is furnished or satisfied. Okay, we are getting the highest profit possible. So that is how we use a linear programming problem. So let us get to this question right now, and we'll solve similar such questions now after this. So the question here is, which of the following is not a vertex in the positive region bounded by y equal to 0? So positive region means it should be in the our feasible region. That's called positive region right now. Okay, so let's just substitute the values and see without writing the graph. That is also one way. If 2x plus 3y less than or equal to 0, so this has to be substituted and checking. We can check, but it has to be satisfying all the given conditions, right? So substitute first value, option A. If x is equal to 0, y is equal to 2, what will happen is 0 plus 6 less than or equal to 6x. Whereas the next one is 0 plus 3 2s are 6, which is less than or equal to 15. Yes. And x is equal to 0. X is greater than or equal to 0. Yes, that is satisfied for A. Whereas B also satisfy if you put 0 plus 0, that is less than or equal to 6. 0 plus 0 is less than or equal to 15. X is 0 is greater than or equal to 0 for both the cases. That is also satisfied. The question is which of the following does not satisfy, right? Not a vertex. What about 3 comma 0? If I check 3 comma 0, 2 into 3 plus 0, which is less than or equal to 6, correct. Okay, 5 into 3 plus 0, which is less than or equal to 15, correct. And again, 3 is greater than or equal to 0, 0 is greater than or equal to 0. That means this also satisfies the given condition. That means what is the answer? None of this. None of these cannot be the vertex of the positive region. What is the positive region? I just show you the feasible region, right? In that graph particularly. So we had a feasible region there. In that feasible region, so this is a region, and all these points are going to be a part of this region. That region is called positive region. Okay, so it is a feasible region. Indirectly, it's telling which of the following points is not a part of this region. All these parts are going to be a part of this region. So can we check this solution by graphical method as well? Yes, we can try that. So it will be a good practice. Let me take a graph again. Okay, so as I'm focusing on the first quadrant, I'm going to draw bigger on this side only. So we have these points. So I can draw the line of value still. It depends upon what value. So let's first take the equation and see where our lines coincide. So if this is equal to 6, when x is equal to 0, y is equal to 2. When y is equal to 0, x is equal to 3. So one of the point will be like this. 1, 2, 3, 4, 5, 6, 7, 8. So I'm roughly drawing the graph. May not be up to the scale. Okay, so but it is easy. If you observe this, you can do the same thing on the actual graph as well. Okay, so let us assume this is the scaled graph. Okay, so one of the line will be going through 0 comma 2. What is 0 comma 2 means here, and 3 comma 0. So this particular first line is passing through 0 comma 2, and let me erase this. Yes, assuming this is a straight line. Yeah, so this is one condition, and it is saying less than 0, so it has to be on this side. Okay. Okay, next what we have is 5x plus 3y is equal to 15. When x is equal to 0, y is equal to 5. When y is equal to 0, x is equal to 3. That is 0 comma 5, which is here, and 3 comma 0. Again, another line I can draw passing through this. Yes. So finally, if the common region has to be this side, because x is also greater than 0, now x is greater than 0, and y is also greater than 0. So if I want to draw this common region now, yes, this is our common region. Just imagine this particular region. This is our common region. Right now, let's assume this is our common region. And where is our feasible point? This is our the corner points. Okay. So now, where is 0 comma 2? 0 comma 0 is here. It's a part of the solution. Yes. 0 comma 2 is here. 0 comma 2 is here. Yes, it's a part of the region, right? Yes. And 3 comma 0 is here. That's also part of the region. Because it is having equivalent to, that is all, these are all the part of the region. That means the answer is none of this correct, right? Yes. Let's go to the next question. There is no objective function given here, so we don't have to worry about what is the maximized, what is a feasible point or optimization point. Let's go for the next part. Shall we go to the next question? Yes. Now, the question is the feasible region of a given linear programming problem. Okay, let's first zoom it out and observe. So hope this is clearly visible now. Yes. So this is the region. Now what we have here is yeah. We can just observe this. We don't have to completely zoom it in as well. So by observation, I can tell you which of the following cannot be the option. We can remove them. So All of them have x greater than or equal to 0? No. So I can eliminate option D because x is less than or equal to 0. This can be eliminated because it has negative constraint and we are looking at the positive side only. Okay, so now I need to look at this B because we have a line graph like this. 1 second. Yes. Just give me a second. There is some issue. Yes. Yes. So now if there is a graph like this, I mean, roughly I'm writing the graph. The graph looks like this, even though I'm not writing exactly the graph. I'm just showing you by observation only how to answer this. So the lines are like this. That means my region has to be more than this. So 0, 0 cannot be a part of this solution. This is our origin, right? So let's just substitute that 0, 0 and check are they satisfying or not. For example, x plus 2y is greater than or equal to 4. So if I put and x plus y less than or equal to 3. So I'll just consider the second one. If I put 0 and 0, it is a part of the solution, but 0 and 0 is not a part of the solution. That's why I can eliminate option A as well. Just like I eliminated option D, I can eliminate option A as well. So coming to second option B, if I substitute 0, 0, which is satisfying the first equation, so this cannot be the answer. So answer must be C only. Let's verify x plus 2y greater than or equal to 4 and x plus y equal to 3, or you can say equal to 4. Now x is equal to 0, y is equal to 2, y is equal to 0, x is equal to 4. So this is our point. Okay, 0, 2 and 2, 4. 0, 4. Okay, next one what we have is 3, 3. This is what it is, 3, 0, 0, 3. So yes, these points are exactly matching for the only option C. So answer should be C. Let's see the option. Yes, C. The answer is option C itself. By observation only, we can answer this kind of question. Okay, so just it needs a little practice. So you need to know all the basics correctly first, then only we can get the answer like this. Okay, so it is not at all difficult if you practice well. This is a very simple chapter. I'm telling you, don't worry too much about it. Okay, so the number of corner points of a feasible region are determined by the constraints. The constraints are given. We have to check the corner points. How many corner points are there? Right? So let's see. So x is greater than or equal to 0, y is greater than or equal to 0. So if I draw the line for the given graph, let's see how does it look like. Okay, so x minus y is greater than 0 means x can be equal to y. You know how this graph looks like? Do you have any idea? This is the graph which goes through the origin. Okay, so and it is having a positive slope, so 45-degree. This graph goes through this. Now it is less than 0, they're telling. So if x minus y less than 0, and x minus y more than 0, that's what it's saying. So x minus y more than 0, x must be more than y. If x must be more than y, so this is the region we're going to have. For example, if I take a number like this, 2, 0, here x is more than y. So here, if this region is definitely a part of it. So our region is here. Our feasible region is on this side of the line. Okay, for this particular equation. Now the next equation is 2y minus x equal to 2. When x is equal to 0, y is equal to 1. So one of the point is 0, 1. Here it is. Okay, next, when y is equal to 0, x is equal to minus 2. So another point is here. Okay, if I draw the line, Okay, minus 2 comma 0. So if I draw the line like this, it will go like this. Let me check. Mm, it will go like this. Okay. So now if I solve these two equations, what we get is, are we getting the point? We have to see x plus x is equal to y, and then 2y is equal to x plus 2. Just to make sure that whether they're intersecting or not, these two lines are intersecting and this is a point of intersection. That means at this particular region, we have got the region which is having a corner point. Which side is a feasible region? We need to understand, right? So where is the feasible region now? 2y less than or equal to x plus 2, right? So if I put, I just want to know whether origin is a part of this or not. So if I just say 2y minus x less than or equal to 2. So x is equal to 0, y is equal to 0. It is less than or equal to 2. Yes. That means origin is a part of this region. That means our feasible region is here. So this is our open feasible region and it's an open bounded region. So it's going to be having two corner points only. So the answer should be option A. Let's see. Is it option A? Yes, option A. So how many corner points are there? This is one corner point and this is one corner point. Okay, what are corner points? These are the points which are going to have a optimized value if there exists a optimized value. So the corner point we have to try to understand. Suppose if we think this is the region, feasible region, we have three corner points, but that's not the feasible region. The feasible region is this side. So the corner point is here. Okay. Yes. So let's go to the next question quickly. Question number, what we have? Question number 4. Yes, the solution set of the equation. What is this equation? In equation 3x plus 5y, we have to go from the option is the whole xy plane. So first let's draw the line accordingly. So a random line I'm going to draw. So 3x minus plus y 5y. So if I write further, 5y is equal to minus 3x minus 7. So the line will be like this. Okay, so it because when x is equal to 0, y is equal to minus thing, and y is equal to 0, x is equal to minus something. Okay, so sorry, this is plus. So y is just let me correct this part quickly. Yes. So our equation is, if I take the equation like this, 3x plus 5y is equal to 7. So 5y is equal to minus 3x plus 7. So it has a negative slope, but positive y-intercept. As it has a positive y-intercept and a negative slope, the line will be like this. And it is not actual line because it is a inequation and we don't have equal symbols. So it has to be excluding the line. Now, where is the region? We need to understand, as it is less than 0, less than 7, x is equal to 0, and y is equal to 0 will satisfy this. So our region is here, this entire half plane. Half plane means on the line, this is right half of the plane, this is left half of the plane. Now the left half is our region, excluding the line. Now can you answer the question? It is open half plane containing the origin. Yes, containing the origin, except the points of the line. Yes, this is the answer, option C. What about option A? It's a whole xy plane. It cannot be the answer. Whole xy plane cannot be the answer. Half of the plane containing the origin except the points on the line. Yeah, this half. There are two halves, right? One is containing the origin, one is not containing the origin. So this half is correct, containing the origin. Along with that, what? Excluding the line. So the answer is option C. Okay. So I hope this is making sense for you now, right? Slowly. Okay. Let's go for the next question. Yes. So here there is no graph to deal with. It is just an optimization function. Objective function is given. Okay. This we have to optimize with the maximization. We have to maximize this. Okay. And yeah, not maximization. They're telling Z max is equal to 42 at 4 comma 6. What is 4 comma 6? The value of x. Okay, variable value. That means 4a plus 6b is equal to 42 possibly. Okay, similarly at 3 comma 2, that is 3a plus 2b, we get the minimum value 19. So what is the value of a and b? See, x and y are variable, whereas a and b are what? They are constants. That means once you know their value, they will never change. That's why we're going to use these variable values of x and y to find out the actual constant value of a and b by solving normally equation method. So when you want to solve this, you just multiply this by 3 and subtract. We get 5a is equal to 57 minus 42, which is 15 by 5. A is equal to 3. If a is equal to 3, we can substitute here. That is 4 into 3, 12 plus 6b is equal to 42. If I solve this, 6b is equal to 30 and b is equal to 5. So that means what? B is equal to 5. So our answer is A is equal to 3 and B is equal to 5 by solving the given condition. So which option matches with this is option, yes, option C. Don't get confused with option D. It is A is equal to 5, B is equal to 3. But actual answer is A is equal to 3 and B is equal to 5. Okay. I hope this is clear. This is same as solving a linear equation with the given condition, right? Yes. Let's go for the next question quickly. Question number 6. So what do we have here? The feasible solution in the linear programming problems is located within which of the following quadrants? So usually feasible region always have a positive constraint like x greater than 0 and y greater than or equal to 0. That means both x and y are positive. Both x and y are positive in which quadrant? That is quadrant 1. So it is always a part of quadrant 1. Let's see the option. Both first and second quadrant? No. First and third quadrant? No. Second quadrant? No. Only the first quadrant? Yes. That is our answer, option D. Okay. See the answer? Yes. Because it's a very fundamental thing to know that when there is a non-negative constraints are there, both x and y are positive. That falls only in the first quadrant. Okay. Let's go for the last question in this introduction part. Okay. So yes, so we're done with the questions in this.